Hello, everybody. Welcome to our PLC2 timing constraints webinar. My name is Eugen Krasin. I'm your host today. Now let's actually start with our webinar talking about timing constraints. Okay, first the agenda. Well, after a short overview, I will talk about how to constrain the clock. You know, the clock is one of the widely used signals in our FPGA. So we need to understand how can we constrain the clock. We need also we do need to understand how we can constrain the IOs, input and outputs, and that's usually the case. We need to understand how to constrain some exceptions, because situation in our real world, situation exists where we have to define some exceptions which are not following the standard rules. There are some specific timing exceptions. So we need to understand how to do this, because when you do these timing exceptions, you will usually this results in shorter run times of your design turnaround time, and you will get better results. Okay, so first overview. So what is all about? Well, in our FPGA design flow, okay, the design constraints which are defined right here, they are used as in the synthesis as well as during the physical implementation. This means if you don't define the design constraints, you cannot expect that the design which you get here will fulfill your requirements, your timing requirements. Because if you don't name your timing requirements, how can you expect you will get the proper timing here? So you have to define the timing requirements. But once you define the timing requirements, the timing requirements will be used, okay, they will be used throughout the implementation cycle, okay? But how can you actually understand, did I met the timing requirements or not? There are actually several ways for you to do this. First one, you just read the report file. So by reading the report file, you can easily figure out, okay, all my requirements, definitions, and all the definition, all my requirements are met. That's one of the way how you can do this. Or if you need some very, very special information for a very, very special path, you are interested in the timing behavior of this path, then you can actually run, it's just a click, okay? You run the extraction of the physical database, and you actually run a tool called timing analyzer. And the timing analyzer will tell you exactly, oh, okay, maybe there's a flip-flop here, it's clocked with a clock A, I don't know, maybe. We do have some logic here, combinatorial logic, and then we have another flip-flop which is capturing the signal. Let's assume maybe it's captured with a clock B, okay? And then because it's something not really correct, you know, maybe because the two clocks are asynchronous. Because they are asynchronous, it's very likely we'll get a timing violation here, okay? And then to understand this, you can actually run the extraction, say, give me the analysis, and timing analyzer will immediately report to you, hey, there's a problem here. You have to fix this. This from the flip-flop called A to flip-flop called B. There's a timing error. You have to fix this, otherwise you will get maybe some unexpected results during the real application. So and now we need, that's all about, okay? And now we need to understand what kind of timing constraints are available here in order to get good results. So that's all about this webinar, to give you an overview. So that's actually the basic idea. So this is my FPGA design or FPGA device. Okay, so that's just as a representative block diagram. So there we have an input called the in, data in, some combinatorial logic. You know, that might be something like this. Then flip-flop here, again, maybe some logic, flip-flop here, and then maybe some logic, and then the output, it's the out. But you know, the FPGA is not alone in the world. This FPGA, for example, will be clocked with a clock B. Okay, but we do have an upstream device right here, which is clocked maybe with clock A, because it is simply a different clock. Now, this is a device from a vendor, from Texas Instruments, for example. Now, you look to the data sheet of this device, and then in the data sheet, you will see exactly this information. For example, there's a signal Q. Here we go. Then this means if there's a rising edge of the clock, in this case clock A, then it looks like this. So this is unknown. So we are not allowed to capture the data here, but here, the green means, okay, the data are stable. And you see the definition, that would be here, the T1 min, this would be the min value here. And no, sorry, this is not the min value, it's the min value is right here. So in this case, after the rising edge here, so this means for the time T1 min, the data is still, the old data are still stable, all data. Then the data will change, but after the max time, which is here, okay, the data are the new data available. So it's also visible here. So data stays for T1, but min, but for the T after T1 max, the data are here. So we need to describe this timing right here. Because we want to need to understand if I connect the clock A with a certain period, TA, to a FPGA with clock B, then it must check, so, is this a clean connection? Will I always capture the proper data here, or is there a problem? And the same stuff must also be done, you know, for the downstream component. So my output signal, the out, is connected again, maybe on a PCB. This is maybe this time T3 represent maybe some delay, some trace delay on the PCB. You can define it. If there's no trace delay, then T3 will be 0. But in general, there is maybe some delay. So this is connected to the input of this external component. But this external component, downstream component, is clocked with clock C. Clock C is not clock B, and not clock A is completely it's a different frequency. Now again, you look to the data sheet of this external device. In the data sheet, you see this timing diagram. This means that there's a rising edge of the clock. Here we go. There's a, oops, sorry. If there's a rising edge here of the clock, here we go. Then this, in order to function properly, this device needs a certain setup time and a certain hold time. So if you make sure you will meet these requirements, then this device will work correctly. If not, you will get an error. So this means this is the basic idea. That's all what we do. First, we look to our FPGA. Here we go. We define all the internal stuff in FPGA. Maybe all the stuff which may be run with clock B. Then we look to all of the inputs of the FPGA, all of the upstream devices, and look which clocks actually used to drive this component. Maybe they are the same, clock A equal to clock B. Yes, why not? And then we need to look to all of the downstream components and analyze which are the requirements here. And then we have to describe all of this constraints. And then we did the job correctly. Just to give an idea how many constraints were here. Let me just clean this up here. So just to give an idea. So for this simple example, we would need, you know, this would be two specification, one for min, one for max time. This will be also two specification, one for setup, one for hold time, and this would be one specification for the clock. This would be maybe a second specification for this clock, and this would be maybe a third specification for this clock. So in this case, in this simple example, we would need to specify 7 timing constraints, 2, 4, and 3, 7 in total. Okay, so this means it's pretty common that for your timing specification you would have maybe 50 timing specification commands. So that's the basic idea. First one is we need to go back. We need, of course, to understand how can I specify the clock. Okay, here we go. So the clock is a periodic signal. So which are the attributes of the clock? We would like to specify the phase, the high and the low duration. This means, of course, also the period, and maybe a jitter, high to low, and a jitter, low to high, because that's a standard part of well, that's our life. So we will do further jitter. So now we have to specify this. So this means that's actually what we will do. The syntax, the command for specifying the clock would be create clock. So this command, create clock, this is some name, this is a username, and you specify the period, and then you specify the object. So what is the object? You know, the object is a connection of this clock to the FPGA. So in this case, you see here, let's look at the definition of the sys clock. This means to my FPGA device, I connected a clock called sys clock. Now I need to specify this frequency in order to tell to Vivado, hey, that's a clock which is actually connected to FPGA. Then that would be this specification. Create clock with the name sys clock. Here we go. The period is 10 megahertz. This means this is 10 nanoseconds. This means this is 100 megahertz. Okay. And the connection is the connection CLK. Connection CLK. So this is the object. This is a connection. But look to this. Look to this clock. Look to this clock called my clock. This clock, my clock, is not connected to the FPGA. This clock, my clock, is just needed to drive the upstream components, which again drives a signal which connected to the in. But this my clock is not connected to FPGA. This means there is no object because it's not connected, so zero, nothing. So this means that would be the specification here. Create clock with name my clock. Here we go. Period is 5 nanoseconds. This means 200 meg, and no object. This means it's a virtual clock. Virtual clock means I need it in order to define this behavior, but it's not connected to FPGA. It's called a virtual clock. So in this case, that would be the virtual clock right here. So a little bit later, you will also see an example. Jitter. So in some cases, you would like to add a jitter to the clock. This means you do have a real life oscillator, but you look to the specification and the vendor of the oscillator tells you, I do have a jitter of 100 ppm or something like this. You would like maybe to take this into account. So by using the jitter statement, you can add a jitter to the clock. And then even define the jitter change and transition from low to high or from high to low. And this jitter will be taken into account during the static timing analysis and calculations. So in this is, you will really get the real case, what may happen as best and worst case in the real world. Okay, latency. You can also define the latency of the clock. Very important. What is a latency? Latency is important. So latency means I can delay a clock connection. It's called the latency. The question is, why should I delay? What's the application for this? Why should I delay a clock connection? Well, let's look to this design. Very, very simple case. Again, this is my FPGA. Yeah, so here we go. In my FPGA, I do have 4 inputs, A, B, C, D. And these 4 inputs, A, B, C, D, are, connected to 4 external devices, and all of these 4 external devices, they might be also of different type, they might be from different vendors, they do have different min and max. This is the timing behavior which is defined in the datasheet. The point is, I do have an oscillator 100 meg, but maybe this oscillator, it's not very powerful in terms of handling in dealing with a high fan out. So I decided to take the same signal, but maybe to use 3 buffers. Okay? So it's the same clock, but one buffer is actually drives this clock, another buffer drives this clock, and this buffer drives this clock here. But the source is the same. So, but the point now is these buffers, they do have even it's the same component, it's the same type of component, their values could be different. The delay, min and max delay for this could be a little bit different, and this could again be a little bit different from this. That's a real world. Even they are specified the same, they could be different because it's from min might be I don't know 2.2 nanoseconds, okay, and max might be 2.8 nanoseconds, and this and anything in between is valid. So they could have really different delays at different time or at the same time. So now, how can we constrain this? Because it's important for us to constrain this. Well, in this case, we just define this clock. We define the clock here, and we define this clock. We define first the sys clock. It's this one with a period of 5 nanoseconds, 200 megahertz, and you see the connection. It is connected to clock. Yes. Now I define the virtual clock 0. The virtual clock 0 is the same period, but there's no connection because this virtual clock 0 is connected to this component, not to FPGA. There's no object. And then I define the virtual clock 1. The I for input, okay, and this is actually this definition here, also virtual clock. So now I do have defined first 3 clocks. Now I set different latency. You see, now for the clock, what clock I set the latency of min T12 and max T12. So this is a different delay here from here T12 to min to T12 max. Then for the output for this clock, I define this latency, and for this clock, I define this latency. Even the clocks are actually the same originally. Now they are slightly shifted to each other and are somewhere arbitrary in this range. Now these clocks again are used to drive this component, to drive the FPGA, and to drive this downstream component. This means everything is changed. We do have a lot of parameters. By the time analysis will calculate everything, will tell you yes or no. That's the big advantage, how we can deal with that. And the next one is generated clocks. So what's a generated clock? Usually, so if I go back here, usually it's something like this. So we just have a clock which is basically connected to my FPGA. So it's connected and is used somewhere. But in some cases, we would need to generate internally, maybe to have a, maybe here, connected here, maybe an object, which again generate maybe a clock X here for some reason. So this means that's an internally generated clock. Now I need a way, how can I define this clock, because it's needed, because it's a clock. So I define a clock, so I have to specify. So this is called the generated clock. This means we do have 2 different kinds of generated clocks. One is a so-called automatic generated clock. This means situation exists where you define a clock, but we rather understands completely what's going on and does everything for you fully automatically. It's called automatically generated clocks, okay? And the second type of the generated clock is manual generated clock. So in this case, Vivado is not able to understand what you are doing, even it's correct, but simply not understand, and you have to do something manually. It's called the generated clock. And I do again. We will see again an example here. First, again, automatic generated clock means whenever you use, for example, PLL to have an input clock and to define several output clocks, then all of the output clocks were completely, including the phase, including the frequency, everything will be done and calculated fully automatically by the Vivado, by this design suite. It's called automatically generated clocks. That's an example. You see, I do have my FPGA, and what I'm doing, very simple one, you see, it's connected, a block is connected right here, 100 megahertz. I run through a PLL, and in the PLL I use the output 2x, so this means I multiply just the frequency, and so the output is 200 megahertz, and then I connect the output here to this object. Now, the only thing what I do have to constrain, this only thing is just, I need just to constrain this one. Create clock, maybe with the name clock, CLK, that's my username. The period is 10 nanoseconds, yes, 1 megahertz, and it's connected to the port CLK, yes. That's all. If you start now, the definition and the implementation time analysis, Vivado will understand, oh, this is a PLL. Vivado look to the specification, to the attributes of the PLL. Vivado will understand, yeah, I generating the clock signal with a double frequency. It will automatically generate this clock signal and use this for the timing analysis. It's very, 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 very nice. And I just to show you, I just prepared, this example here. That's my notepad. You see, that's actually what happened. This means the clock is something like this. But because I run to PLL, I will get the clock out, which is, of course, I have double the frequency. Okay, but it's done fully automatically, and this is applied to the counter and will gives you the analysis. This means if I look to the Vivado, so I define the Vivado. By the way, if you like, you can get all the examples. Just send us an email, you will get all the examples. So this example one, I call this example one. If I look into the, you see, it's a clock, is the input, count is the output. Here we go. Clock is the input, count is the output, and that's the FPGA, okay? And then I do have a IP called, I call this PLL. You see, clock in is the clock. I define just two clocks. One is a 100 meg and one is 200. So I don't need actually 100, but I just defined it. Then I have a counter, okay? And then I define the two clock signal. One is 100, one is 200. And I just connect the clock to the PLL. The input clock, you see, clock out one is a 100 megahertz clock. Clock out is a 200. I don't need the 100, just defined it just as a demonstration. So then I use the 200 megahertz clock. Here we go, and connect this to my counter. Now, if I just run the elaboration here, then you will see the structure. And then if I actually run the analysis, then the Vivado will tell me, yeah. First, Vivado will tell me there are actually two clocks in your system. Actually, will tell me there are three clocks, because one is a definition of my external clock, and then two internal clocks. Even one clock is not used. So now you see that's elaboration. You see that's the instance. So if I open the instance again here, maybe you see that's actually input clock 100 is a PLL. The clock out 1, it's not used because I didn't connect it. And this was a 200 megahertz clock. And you see if I select this, it tells you this 200 megahertz clock. And this is the counter, which basically runs with this 200 clock. This means the timing constraints, which I defined, is actually here. So this is a constraint. Here we go. Create clock with a period 10 connected to clock. It's the first, this is one and only actually definition here. So I could actually go to the tickle, and I think I can do it right after the elaboration. I can say report clocks, okay, and then if I report the clocks and I look scroll up, then he tells me, okay, clock report. He tells me, yes, in your design you have a clock which the input. You see, P stands for primary. Then you have one clock generated by the PLL. It generates you 100 megahertz 10 nanosecond period. It's based on the propagated clock because the input, but it's G generated and A automatic generated. Then next clock, this because it defined 2, with a period of 5 nanoseconds is a 200 megahertz clock again. And the third one, that's the reference clock for the PLL. So you see immediately that's actually the definition. And now when you run this, maybe I have enough time later, then you can run it. Then you will get the analysis, and the Vivat will tell you yes, it's okay, or no, it might be not okay. Okay, so let me. Okay, so now here, this one close, and so this was very nice. This was an automatic generated clock, but sometimes we need to define a clock which is not understood by Vivado. So we have to do it something manually. It's called the manually creating generated clock. So why? And what is the reason? Why should I do this? Well, for example, this one. Let's assume, oh, maybe first information, inside the AMD's FPGAs. So we do have several different clock buffers. One clock buffer, look for example, something like this. So it's just a clock buffer, you know, there's an in and there's out. Easy, nothing happens. So this means in and out. Okay. But in some cases, you would like to decimate the clock. That's called to make it slower, the frequency, to make your frequency slower. There are a lot of reasons to do this. For example, reduction of the power, optimizing the power consumption. So in this case, you have another clock buffer looks like this. Okay, looks like a tri-state buffer, but it's not. So this is again the in, this is the out, and this might be the enable. Okay, and now, for example, if this is the in, and then the enable, maybe enabled maybe here, something like this. Then this would be the in. Then the out, you know, would look like this. So you decimated the block. So in this case, it's 1, 2, 3, 4 by 4, and this is exactly this guy here. So that is internal very special clock buffer called buff GCE. So this is the called buff GCE. Now I take a 100 megahertz clock and just connect it to a counter which this counter runs. Counter A runs with 100 megahertz. Okay, nothing special. But this guy is used as follows. First, I defined just a simple 2-bit counter which divides by 3. It's exactly this. So divide by 3. 1, 2, 3, divide by 3. Okay. Change the enable pulse. This enable pulse is actually used to enable and disable this clock buffer. So this means a resulting signal called clock TIF is right here. So I'm use this as a clock signal to run the counter. So in my case, I defined the enable divide by 3. So this means if this is 100 megahertz, and this is the PLT is 3 times bigger. So it's 30 nanoseconds, it's 33 megahertz. So you see, that would be the specification. First, we define the clock because there must be known. And second, now I define exactly this clock. I say, hey, that's a generated block. That's what I did, because Vivado has no idea what I'm doing here, because Vivado doesn't understand here this function. Vivado doesn't know what is the timing of enable. but I have to tell it. So in this case, say, well, I would like to define this clock called clock diff. This is just the name. What is the source? Well, the source is this clock. The source is this clock, this input port clock. Here we go. This is the source, the clock. And this source is divided by 3 multiplied by 1. So this gets multiplied by 1. I don't have to specify this because by 1, but I did it. Multiplied by 1. And what is the name of the net? And I would like to constrain this way. Well, it's the net clock diff. Okay, so now, say if I do here, then during analysis, this counter will be constrained to run with 100 megahertz. This counter it will have a very, very relaxed constraints because it only runs with 330. So this makes it very, very, very easy. So let's assume. So in this case, the counter, let's assume that might be, I don't know, a 16-bit counter, which can easily run with 100 megahertz easily. But this counter, just let's do it 100-bit. Okay, so this 100-bit counter will not, standard binary counter without any tricks, will not run with 100 megahertz. Okay, but maybe you don't need it to run with 100 megahertz. You don't need this high resolution. It would be enough for you. You need 100-bit, but you don't need the resolution. So in this case, you just go decimate the clock. Now this counter will run with 33 megahertz, and now you will get a proper result. If you don't do this, Vivado will try to optimize the 100-bit counter to 100 megahertz, and this is impossible. So the implementations often will fail, and that's all about. So this means what we have to do all the time is to do actually the timing, the static, so-called static timing path. And what is the static timing path? That's what you see here. The static timing path is from flip-flop to flip-flop. That's the one and only path which exists. It sounds not correct, but it is. Because if this is FPGA and this is the only path, one and only path, I can easily prove you that's how all of your designs look like. Because if I just connect a upstream component right here, okay, then you will have the same path again here. If you connect a downstream component right here, it's the same path here. So it means the path time is always the same because it's the one and only path we are talking about. So in this case, we don't care, is the clock the same or not? It could be the same clock, but it could be completely different clock. We don't talk about the clock. We just talk about register is talking to register. This is the one and only path which exists, you know. In this case, let's say it's on flip-flop or the register, let's say clock element. But which clock element, what type of clock elements exist in FPGA? Well, flip-flops, clock ramps, and DSPs. So this means all registered elements. So this means all elements like combinatorial elements like lots in multiplex, whatever. Huh? So this means this is here the symbol for. They are not part of the they are included in the past, yes. But you will never mention this. You will actually always say from here to here, and Vivado will take everything inside and will optimize. So in my example here, the path from here to be maximum of the type TB, whatever this is. So that's actually the point. So this means that's really what happened during the implementation. Vivado, we define a clock here, and then maybe we define also some timing from here to here. So this is a starting point. This is my FPGA. Once we define this, it's the only information which is needed by Vivado, the clock and the day in. Then all the other stuff like delay, so the combinatoric delay on the nets, clock to output delay here, everything else is known by Vivado because the implementation is done, all the delay information is already there, and now Vivado starts the analysis. It looks difficult, but you don't need to really, you can do it. You can really take a piece of paper and just calculate the values, but that's actually what Vivado is doing for you. The only thing what you have to do, you are just responsible for defining the clock And optional, define the time behavior of the in. That's all what you have to do. Yeah. Then by using this definition, so now Vivado does exactly understand how the clock looks like. So in this case, 5 nanoseconds period. Okay. This information is used to calculate for all of the flip-flops the setup time. Okay, because all of the flip-flops, all of them, have two potential errors. Could be a setup time error or hold error. So the first step, all of the flip-flops are checked. All the setup values for all of the flip-flops are checked. And there must be, okay. Then the next step, now all of the hold values of the register are checked. So first the setup check setup time must be met and the hold time must be met. And only if and when both types are correct for all of the flip-flops, then Vivado will tell you, yes, the timing, the requirements are met, and your FPGA will run in the real application and in the real world. So I will a little bit later do an example, but now we need also to constrain the connection. It's called the input and output. So we need to constrain the IOs. So in this case, this is my FPGA again. So let's talk about the input. So we do have a device right here, which is maybe clocked with this clock, and it's connected here to the FPGA. Now, we do have a clock, it's here, maybe around this 100 megahertz. You see what is very special here? Very special, it's called system synchronous. System synchronous means I do have one clock, which is used to clock the external upstream device, but also the FPGA. That's a very, very common situation. Now, in this case, we have to define, this is indicated by this pass here, the clock to output behavior of this component, and we have to specify the clock, and then the Vivado will completely calculate completely autonomous all the values. So this means in this case we have to specify this. So this is the clock. So let's call the signal Q. So what happened in the real world? Then you can get this information also from the data sheet. Signal Q looks like this. This rising edge. Then after a while, the signal Q will change. It will be unknown, we don't know. But then it will, and this will be repeat, it will repeat again. So here we go. Yeah. And then for the next one, so this would be the period T for the clock. And then now you get from this, let's say this is from Texas Instruments vendor. Yeah. Then the Texas, some component, some chip. And in the data sheet, you see this information after the rising edge. For the time T1 min, the data are still the old data. So these are still the old data. This will be the new data. Then after the time min, okay, the new data will appear after the time T1 max. So this could be, I don't know, 2 nanoseconds, and this could be 4 nanoseconds. And you get this information from the data sheet of this device. And you basically put this in, and that's it. And that's actually all about in this section. So this means, okay, but there are two situations. First situation is system synchronous. Then we will do the example, system synthesis. System synchronous. This means that we have one clock which is used for both components. And in opposite, we do have also the possibility to have a source synchronous system. So what does it mean, source synchronous? This means the source which provides the data is also providing to you the clock. You see? So that's very, very typical situation for fast ADCs. So I do have a very, very fast clock here. I don't know. This fast clock is used for, you know, for sampling all the data, and then it's serialized, and then it's sent to the FPGA with a very specific clock we generated here. So this means the data and the clock are synchronous to each other. So that's called the source synchronous application. But in this case, the FPGA needs a receiver which actually has this clock and the data. So, but in this case, of course, the FPGA must also have some kind of a sys clock, because this sys clock is the clock which is used to do some, maybe, you know, to do something else here, okay? Because this is just for the receiver. But the further processing, of course, you cannot use this clock. Maybe they switched off after the, you know, after the transmission is done. Maybe the clock is switched off. So therefore, you need usually two clocks. One is for receiving and one is for the system. So, but it's called source synchronous. So in this case, that would be again the input specification. I do have the upstream components, so I have to define this. Again, let's assume I have a clock A and I have a clock B. So we define the clock A, and again, you looked at the data sheet, we define T1, we need T1 min, and we need T1 max. That's the timing value which will be found in the vendor's data sheet. Then for the next section, next part of this next section, we will look to the output. So in this case, we do have clock C, maybe again another clock, which is actually driving the downstream component with a setup and hold requirement. So that would be the setup requirement, that would be the hold requirement. So in this case, I would have actually 3 clocks in my system, and of course, I have to define everything. And that would be again the general form is we do have a source synchronous and we do have a system synchronous. These are the two situations which we can actually face during our implementation. So this means, again, this is the key for the input. First, you do have again the FPGA here, and they have an upstream component here, and they have a clock. Could be the same clock, I don't care. Could be another clock, and then it's connected somehow here. But you have to define exactly this value. If there's a rising edge, for example, or falling edge, both is possible. If there's a edge, you know, the clock edge here, then what's the behavior of the signal? So what is the minimum value and the maximum value? So in this case, you see, in this case, at the rising edge, it takes 2 nanoseconds, and then the old data will disappear, and the output will be unknown. But latest after the 4 nanoseconds, this is the max, the new data here. So that's this, and this behavior must be specified here, because when later, so this is a pin day in, for example, of the FPGA. Later, you define the clock. Now the FPGA knows the clock. The FPGA Vivado knows the timing of the data in, and it will tell you exactly, yes, I am able to capture this data properly, or no, I cannot. Okay. That's actually the point. But why do we need 2 delays? Why do we need a minimum and maximum delay? Well, the maximum delay specification is used to check the setup time of the flip-flops, which are receiving the signal. And the minimum value are used to check the hold time requirements of the capture flip-flop. So that's the reason, because we need to check both of these values. We need to specify also both of the timing parameter, min and max. Okay. So again, that's example system synchronous. That would be exact the specification we need to do. First, we define the clock. Here we go. So in this case, we define the clock to be 200 megahertz. That is the specification. Second, we define the specification of the max. So in this case, set input delay. And what is the value? Well, this is the max value, because it's a keyword option max. It's some value 4, for example. Get port X. This means I do have of the port X, here we go, ein delay, maximum delay of T max, and this is in reference to the clock. And now the mean specification. You see, for the same port, yes, there's a mean and max. Here, it's a, there's a mean and max value, okay? Because it's the clock here. So this would be the mean value. And this would be the max value, yeah. So on the same line, and then we find the mean value. So this means this flip-flop, see, actually 3 specifications. One is the clock, one is the latest time point, and one is the earliest time point. The latest time point is used to check the setup time. The earliest time point is used to check the hold time, and the clock is used to do the calculation. Then we'll say yes or no. Okay, that's the point. And for the source synchronous, it's actually the same here. The only difference is you define first the clock for this clock. It's because it's generated by the external component, so define the clock here. This is seen by the FPGA as input clock. Then you find the system clock, because this clock is just used for receiving capturing the input data. And then you define the input delay again here in reference to the clock. You see, of course, you define the timing in reference to this clock, okay? Because this clock is synchronous, not this. This clock is actually used, for further processing. So usually you would need, of course, here, just in order to avoid CDC, you would use maybe a FIFO here, okay? This FIFO will run from the side with this clock and from the other side with this clock. So you just transfer the data, okay? So that's actually typically very, very typical situation. So this means for the output, we define now this one. So you see, now we are the generator, so the FPGA, and we are connected to the downstream component again. Now, we define again, this is again system synchronous, the clock. The clock is used for the FPGA, but it's also used for the downstream component. The finish is done here. And then now we define the setup and hold requirements. So max is the setup time and mean is the hold time. We define these two values in reference to this clock. Again, go to the vendor data sheet. You will find exactly the values setup and hold. And you put this right here. Okay. So, and for the source synchronous, you do actually the same, but it's a small difference. Okay. But we talked already about this. This one FPGA. In FPGA, maybe I use 200 megahertz here to do something, maybe high data transmission, whatever. And then we just transmit the data, but internally to maybe we generated our own clock called clock X. Okay, but this is generated inside FPGA. So they are not using the signal. Clock X internally is a clock, but this signal clock X is used here as a clock in our system. So now we do have to do the same, what I already explained. We do have to define a generated clock, because this is a generated clock. Because this is a signal used as a clock here. So we have to define this as a clock. So first we define this clock, it's this one. Okay. Now, they generated clock, then we say this is the name is clock X, okay? And it's based on this clock. The source is this clock, because we do something, maybe divider or whatever, okay? And so we do have some relationship from here to here, maybe divided by 5 or whatever, okay? And it's connected to the port clock X. So now we define exactly, well, this is a generated clock, which I defined in FPGA and is actually here, is outputted by the FPGA and the clock X, the port clock X. Here we go. Now, this is already known because this is a port pin, T out or whatever, and this is a clock X. Now we define actually this behavior like here. Set output delay in reference to the clock X. So this is because this is clock X. In reference to the clock X, have a maximum setup time, whatever value TS, and minimum whatever it is, hold time. So that would be the definition for the whole time, for the source. And again, I already mentioned this just to review. We do virtual clocks, which are very important. Again, this might be, again, a summary for this one is very common situation. I do have an FPGA, and I do have actually a clock B, which is actually a clocked FPGA. Then I do have as upstream components U1, which is driven by clock A and have a certain timing behavior. It's connected through this pin to the FPGA. And I do have a downstream component, maybe called U2, okay? With a certain timing requirement, and this component is clocked by clock C. And now I have to specify this. So that's the specification. First, I create a clock A. You see this one is a virtual clock. It's exactly this one, virtual clock. Then I define the clock B. The clock B is this one. It's this one. Okay, this some value. Then I define the clock C. It's this one. This some value. Okay. And now I define the set input delay. I say, okay, I said set input delay is this one, or this, because the input, so this is the input, always from the viewpoint of the FPGA. So set input delay. So you see the input delay is in reference to clock A. That's a reference to clock A. The reference to clock A, you define the min and max value. So these are two specifications. And then the same for the output delay. So this would be the output delay here. It's in reference to clock C. And you define again the min and max value, which are set up and hold. That's actually the complete physical implementation. By the way, all these examples, so you know, example 1, 2, 3, I have all the examples, and if you like, I just show it to you here, you see, and if you like, you can actually here, so we will send it to you if you like, and then it looks like this. You just go to, you see, I want to, for example, this would be what is it? This is example 3. Okay, here we go. You go to this, let's say example 3, right click, say set a stop. Now it's stop level. You see, top level, and now in the constraints, you see, you said that I don't need this one. This is disable. You see example, now enable this file, and now you see that would be actually exactly this design. Simple end gates or something like this. And you see here the constraints. You see, that's the definition of the period and all the subjects. So you can actually take this as example, run, and we'll see exactly the behavior of what we discussed here. Just send us an email, you will get it. Okay. Here we go. So, and then actually, the last chapter is time exception. very simple actually, but could be, but have a lot of applications actually can be done with this exception. So we do have, let's say, for example, one is a multi-cycle pass, a false pass, mean delay, and max delay. Okay, and again, I have also example here. Again, you can get it, and you can actually run it. Okay, so this means, okay, 1 second. What is a multi-cycle pass? Multi-cycle pass basically, let's look to the valid. So I have here the clock. Okay, and then and this is just to show you the valid signal could be something like this, you know. Take the valid maybe here, something like this. So I don't care. You see what happened at this time point, exactly at this time point, the data are actually captured here because valid is 1, clock enable, and the data captured here. Now this valid signal is actually, you know, act as an input to the shift register. This means after n minus 1, whatever this is, n minus 1 registers, the signal appears actually here. Let's call it x. So the signal x appears maybe here. Okay. So you see what happened now? At this time point here, the data which I captured here now will be captured here. So this means I do have in this case exactly the time 1, 2, 3, 4. I do have 4 times t. T is the period of the clock. 4 times t time to get to run from here to here. So I do have multiple cycles time to run through the path. This is why it's called multi-cycle. Okay, so in this case, this example it would be multi-cycle of 5 or whatever it is. So this makes your life very, very easy. So you can create a multi-cycle. You can basically, you can say, okay, from the flip-flop FF1 to flip-flop FF2, you do have 5 cycles time. And then this specification is relaxed. And we want to say, oh, okay, I don't need to hurry. I don't need to make this possible in 200 meg. No, I can have actually 200 divided by 5 is 40. So I do have actually 5 clock cycles time to do the job. So this makes it fast, very, very easy. So again, then in this case, we can create a multi-cycle path. We say path set from A to B, just, and you define not a time value. No, you don't define the value 10 nanoseconds or 20 nanoseconds. You always define the number of clock cycles. Okay, then whatever it is. And then just to mention, you would see this is my example. If you do this, then in this case, say if you don't use the multi-cycle, then you capture the data here, and the data must be captured on the next flip-flop and the next edge. So you have this one cycle time. But if you say I have a multi-cycle of n, then you actually say don't capture data here, just shift it to the new point, and this will be the multi-cycle. So this means if you shift this new point, what happened? You need also to shift the hold edge. So that's actually mentioned here. So you see, you should look to the manual and actually see that whenever you do a multi-cycle, okay, you have always to correct the, but you will see this actually also in my example, correct the hold edge. So this means here, very simple one, example 4, you can actually have it. Again, I have a counter, and I have here, let's say, here we go. I have 400 megahertz. And I have counter A. Counter A is 16-bit. I think it's 16-bit. And it's the counter A 16-bit is able to run with 400 megahertz. It's not a problem. But my counter B is 60-bit. So it's a big counter. Okay. So the counter B will not run with 400 megahertz. But I don't need it because I have an enable. You see, I define an enable, which is, let's say, here, from here to here. So this is the multi-cycle of 1, 2, 3, 4, actually 5 here, okay? Multi-cycle of 5. So this means the counter will count, you see. The counter A is counting every clock. But the counter B is only counting here from x to x plus 1, and again here to x plus 2. So this means you have 5 clock cycles in between, and therefore it's very easy to implement. So this means if you describe this circuit, but you don't describe this, okay, you just don't do it. You just set the clock to be 400 megahertz. Then the Vivado will fail because Vivado doesn't understand this. Vivado will try to optimize the counter B 60-bit to run with 400. This is not possible. This is impossible. It is possible for A, but not possible for B. This means it will fail. It will tell you, I'm not able to do this. So now, but if you say, okay, but the counter B is it's a counter. This means internally, all of the flip-flops are connected to the enable, all of them. So this means flip-flop to flip-flop, or there are always 5 clock in between time. Okay, you say now inside from all the cells flip-flops inside the counter, to all of the cells in this means all of the flip-flop inside the counter B, they have a 5 multi-cycle available, 5 clocks. Then it gets done. Then we get immediately the result, very, very easy. Everything works. So that's the whole idea. Okay. And then we do have a false pass. Again, you see this in my example before, if you like. Creating a false pass. False pass. This means I don't like this. I don't need this pass at all. And so in this case, for example, you say, let's assume for some reason at a given time point, you see, I know. Maybe you just this is a circuit here. Maybe you have a first to configure it and then to run it. So this means during configuration, this signal is to a 1. So this means because of 1, then something is done here. But that could be for example very slow because I don't know, maybe the clock, you change the clock to a slow value, whatever. But then in the real application, it needs to be very fast. But you know, before you start the real application, you just write a 0 in this register. So this register is 0 because register is 0. This pass will never be activated because it's a select 1. But you know it's 0. So this means this pass simply doesn't matter. So you can say ignore it. That false pass. Sorry, this was the wrong one. So this was therefore ignoring this pass is Z false pass. Here, this is the second definition. Through the pin of max A, pin 1. This means all signal which runs through the pin, just ignore it. This means the whole pass will be ignored because no timing needed here. And because it's ignored here, okay? Therefore, also this path should be ignored because this is a static. You did this one time and then the value never changed. So it's static, there's no delay. Then you also ignore the path, this one. It's from register flip-flop, register A to register B. Here we go. So you see, you can do a lot. Or you can do something like this. Again, CDC, clock domain crossing. Okay, you do have maybe clock, I don't know, clock A, whatever, and this might be clock B. It's a completely different clock. Okay, so this means it's asynchronous signal. You know this asynchronous. Therefore, what you do here is a sync. It's a sync for CDC, clock domain crossing. So this is absolutely okay. This is good, but Vivado will try to optimize this path, but this doesn't make a sense at all because they are asynchronous. So this means now we have to actually disable this path in order to save, a turnaround time and make it possible. So you can say Z clock groups, which is the same, Z clock groups asynchronous, which is equivalent to a false path. Z clock groups asynchronous from clock A to clock B, and then this path will be automatically ignored. You can also say Z false path from rack A to rack B1. That from here to here it would be the same. Or look to this application. So we do have a clock multiplexer, for example, now FPGA, clock A and clock B. So this means if you switch to clock A, you will get a clock A here. If you switch to clock B, you will get a clock B here, something different. But you know what happened? If you, for example, so this is A. So this would be, then you switch maybe right here. This would be the select. And let's say just to make it and the B might be maybe the clock B would be here. This would be the clock A. Because Vivado sees also this situation. Okay, something like this. So clock A is fast, clock B is not so fast. Now you switch here. Clock, the output is clock A. Okay, the output is clock A. Then that's okay. So clock A is here. Now this edge is used to capture the data to flip-flop. Yeah, but then before this, then you switch with cell. You switch to clock B. Now the clock B is here. And this means the data which were switched here with this edge will now be switched, captured here with this edge. But the time here in between could be 10 picoseconds. So this means it's impossible to achieve, impossible. Maybe you even don't need this, because we can say, well, during switching, I just keep my circuit at reset, whatever. So then you should say this, that clock groups, they are logically exclusive. Group A and group B. Logically exclusive means they are never, don't analyze the situation where the clock A and clock B are actually on the line, right at the same time. They're logically exclusive. There could be physically switch, yes, but logically don't do this. Don't use this. So in this case, then it will be analyzed just clock A, yeah, or just clock B, but not the switching behavior between the flip-flops. Okay. And then finally, min and max delay, which is very good for example, to do this. For example, again, for CDC, you would like to minimize the delay here. Even you run this clock B, let's say 200 meg. 200 meg, this means it would be 5 nanoseconds. But you know, maybe from the CDC theory that the short time here means better quality. And then you can basically override the 5 nanosecond by saying that max delay from here to here to be 2 nanoseconds. You just override the 5 to be 2, makes the requirements much harder, makes the time much shorter just for this connection from here to here, and this gives you this makes your synchronization better quality. Okay, and the same can be done, of course, for this pass here. Yeah, so in this case, say that max delay from here to here, maybe from red A to red B, 5 nanoseconds. Okay. Or you can ignore it by using clock group asynchronous, complete ignore, or false pass, just this. Ignore. That's what you can do. Oh, and finally, you can actually using min and max delay actually to have an FPGA, no clock at all, just constraining pure combinatorial pass from A to B, whatever this is. Okay. Yeah, thank you very much for all the questions. And my next webinar is somewhere, let me check, somewhere here. I think my next webinar is here. So my next webinar should be, yeah, here we go. That's today, part 1 of the VHDL. Then part 2 of the VHDL, then part 1 of VHDL simulation, and part 2 of the VHDL simulation. It's also very nice, actually. I also will prepare some examples for you doing this, and all of the webinars actually recorded. I do have fall webinars. I do have examples, so you can have it. Okay, good. Thank you very much. I wish you a good time. And I hope I see you next time again. And thank you very much and goodbye.